So we have available the Era 5 reanalysis, which is provided by the European Weather Agency. And it's worth noting that this is a simulation. So a simulation basically means going from raw weather sensors, right, like satellites, like globes, things like this, or like ground measurements, to the kind of an estimation of the true weather state. This is still based on classic physics, and this is not based on machine learning. So we take kind of an estimation of this and reanalyzed more than 40 years back. So we have a massive data set. In terms of size, and that's why that's one of the key factors in deep learning typically. And it's also very high quality data because there's been a lot of compute effort gone into amortized into this data set. The second key factor is compute. As you know, it's now more and more useful for getting performance, and in particular we train on 32 TPUs. And this just goes along the line of increasing scale in machine learning models. Our model itself is quite small, but as I was saying, each input-output example is very, very big. So we really need the compute. But note that this compute is different than the typical compute in weather models. So before, weather models were using servers of around 10,000 CPUs. And now we just use a few TPUs in order to train. And at inference time, we only need a single TPU, which for non-Googlers is essentially like a high-end GPU. And we can do in 1 minute what it used to take a server around 1 hour and thousands of CPUs. And this is because, again, we leverage parallel compute. And the third thing is progress in deep learning algorithms. In particular, we build on graph neural networks. So essentially, we are going to build a mesh around the Earth and think about this as a graph. And essentially, the weather is going to inform nearby weather states by passing messages along this graph. So the kind of short story of how graph neural networks work is they have a latent vector on each node in the graph. And they also have a latent vector on each edge in the graph. And nodes inform their neighbors. And so they update their own latent vectors by sending messages to nearby neighbors and then updating themselves based on the received vectors. So why do we build on graph neural networks? They have, in particular, key inductive biases that we'd like from weather. One inductive bias, for instance, is locality, because nodes only send messages to their neighbors. We are essentially encoding the fact that weather is local. And so in a short period, the weather in London is only mostly going to depend on the weather in the UK. It's not going to depend on the weather in Brazil in a short period of time. And the second thing is equivariance. So that means that because we reuse the same parameters, the same neural networks on all the nodes in the graph, we're essentially encoding that the weather function is the same in the UK than it is in Brazil, than it is in Africa. And that allows us to be much more parameter efficient than if we didn't encode this inductive bias. Of course, these three key factors have been playing on the entire community, not just us. So, so there's been progress in weather using CNNs, also graph neural networks, Fourier neural operators, as well as transformers. And it's really been a wave in weather prediction using deep learning to improve upon classic physics. So let's go into more detail on how our GraphCast, our model works. In particular, we receive an input weather state, and we are going to predict the next state, in particular 6 hours from now. So by using GraphCast, which here it's shown as a black box, but it consists of 3 parts. So the first one, the encoder, is essentially going from the grid, which is, as I was saying, you should think about it as kind of an image, so a rectangular image. But this rectangular image is not uniformly distributed around the Earth. It doesn't know about kind of the spherical properties, the spherical geometry of the Earth. So we have to map it up to a mesh. And so this essentially informs locally the nodes on the mesh. Then we use a processor, which essentially propagates the information around the mesh and informs and predicts a latent vector that informs about the next state of the weather. And finally, we go back to the grid because that's where the predictions are needed. And so we have a decoder that decodes from the mesh back to the grid. This mesh that I was telling you before is actually what we call a multi-mesh. So essentially we have a few edges that propagate the information very far and many edges that propagate the information locally. And how this is made is we take an icosahedron and we iteratively divide each triangle into 4 smaller triangles, and we do this up to 6 times. And so we're going to have kind of a few nodes that propagate the information far, and then many edges that propagate the information locally, and we kind of pull all these type of edges together, resulting in more than 40,000 nodes and 300,000 edges. Finally, we have autoregressive training. So the idea is that the weather function now is going to be the same as the weather function in the future. So really, if we want to predict 10 days ahead, we don't use a single neural network call that predicts directly 10 days ahead. What we do is we predict 6 hours at a time, 40 times, and we train for this autoregressive training. So essentially applying the function multiple times to work well. Our training loss is